Hello. Hmm. Oh god, it's too hard. I don't know. There's three watching. I'm listening to a podcast and it's funny. Oh, look at that. Oh, it's hard. I don't know. Maybe I should try to think more instead of just randomly changing the shader. So the problem I'm dealing with right now is that so I have a color map that can be queried, can be sampled to recreate the missing highlight information. But as you can see, if we apply this trick, this technique as is, we're seeing that this, whoa, no, not this one. We're seeing that the clouds are too blue as they adopt the color of the sky, which doesn't look very right. So I was trying to come up with better techniques to try to infer the color better. And I just feel like this is a thing that I haven't looked into enough, didn't think about deeply enough to correctly do it. So like I can quickly re-show what the initial problem is. So this is the actual data that's sitting in the photo. The pink clouds are effectively what is in the picture. And then as well, like how the sky behind it gets darker, less saturated, is also an effect caused by that, because if we visualize where the sensor is no longer recording accurate data, everything that is not black has a wrong color. Like this, and then so we try to infer the color everywhere it's not black. We have wrong color information, so we try to replace that color with color information of the surroundings. But as you can see, the information gets taken from the sky, which is blue, and the clouds aren't blue. They are supposed to be white. So what we're seeing is that the sky is deciding the color of the clouds, which is what we see over here. The clouds get pretty blue instead of white. And then on the other hand, the clouds near the horizon here kind of adopt the color of this landscape below it, and so like these are having a very warm tone to them, which is of course undesirable. As you could see, there is a tiny patch of information near the clouds right here that has accurate cloud color in it. So if we were to look at what that color looks like, that is effectively yeah, like gray. So that is good, but yeah, it gets, and that's the color that we want, and but because the patch is so tiny, it doesn't win in the fight for the surroundings, because the sky is so big that it stretches out further into the clouds. Yeah, and I can counteract this effect by going into the blur shader over here, and making sure that the blurring process respects most of the local color like this. But then we're gonna start seeing harsh edges around, like areas where one color fades into the other, like this. So you can definitely see that the cloud is now wider. A bigger area of the cloud is wider, but all of a sudden there's a harsh edge. And the same is happening down here. So if we visualize the color map that we're having, it's not gonna look too good. So this is alright. So you can definitely see that the cloud region is indeed neatly like gray, neutral tone. But then a lot of information from the scenery below it gets leaked into the sky, which was a thing that I was trying to prevent by making use of how do I put it? I'm making use of the luminance of the color of the pixel data. So like darker regions get less influence. Let me reset the number of blur passes to what it should be. There's 3 people watching. Be most welcome. So yeah, now even the edge is even harsher. So what I was thinking is that maybe I should prioritize the neutral tones more in the weighing. But yeah, I don't know. I could try experimenting with that a little more. That's over here, so let's repeat this trick twice and let's see what it gives to like know in more extreme circumstances what it will give. Yeah, it doesn't seem to be influencing the result that much, which is not really what I was hoping for. Yeah, I mean, I wanted to have seen more of a change that... See, like this area is good, but everything around here is just bad. I don't know, it's hard, and I think maybe I should look at the original photo and see what the JPEG did, because the camera does have a JPEG thumbnail embedded in it, which could tell us the color that the camera reconstructed for this. Let's see. Let's try Ranger for once. So pictures, France, and then wait. Is this only the videos? No. Okay. So the photo is 4,310. This one. Let's open it. Okay. So you see, the camera didn't have a fucking clue on what to do with it. It's completely clueless. Wait, but this is fair. This is not open AO. Does that work? I don't know. Exec AO. Huh. Help. Key bindings, commands or settings. commands. Change cd, bulk rename, alias, change mood. Just open something. This command opens. No. Open console. It open console. Open. Open with. Okay. So as I was saying, the camera didn't have the slightest clue on what it was doing here, which is kind of like the cheap way out. You can clearly see that we have a lot more detail going on. The color is just not too good. Compare those two. The difference is amazing. There's a lot of detail in the clouds there. That is incredible. That is incredible. So then I was trying to use this trick to neutralize some more of the colors, but that is not working. Let's try the other one. That is kind of neutral, but it's a complete hack and it doesn't look good anyway. But look at the difference. We're having a fair amount of highlight recovery. Well, I think even the rooftops over here lose their color. Let's check that. Disable this hack. Yeah, the rooftops are also influenced by this trick. You could, yeah, like if I disabled all of the other processing. If we were to, like, this is like kind of what the camera did with it, more or less. Something like that. Which, yeah, is a mess, of course. And if we were to do nothing with it, this is also a bit more like what the camera did. I don't know, it's hard. So looking at the clouds at the top, why is that red not influenced by it? Why is that red not influenced by it? I want to see it saturate all the way. Why is that happening? I'm slightly confused as to what is happening with the reds. At a certain point, they're not changing anymore, which is completely not what I expect to happen. They should just converge to one. Let's see what the shader does in the Reinhardt thing. Are we clipping this? Because maybe that is a problem. So let's take the minimum of that. Wow, that did a whole lot. That did a whole lot, and I'm not sure why. Ooh, look at that. Look at that. That is what I was expecting to happen. But I'm just confused as to why. So if this thing is bigger than 1, what comes after it, and why is this influencing it that much? We're applying the curve. Sure. Maybe the curve is... Yeah, see, that's a nice thing. Let's... Okay, so we're on to something bad here. We're closing in on a bug. Let's bring this up again. So there we have the issue. And now try to figure out what effect is responsible for creating this. I could imagine it being the curve, although it's straight right now. Oh, so that definitely did something. Wow. Wow. What is happening? Why does this remove like... Okay, I think I know. So the curve is not clamping it anymore. So now something else is causing problems. For example, the contrast. Contrast is a very good one because, yeah, it's probably going to be contrast. There we go. There we go. It's the contrast is the problem. Look at that. Okay. This is detail enhancements in the sky. Okay, so right now, and okay, so the contrast really demands that the things should be clamped. And if things are not clamped, then the contrast function is bugged. But the same can be set for the curve, actually. So right now, see, alright, so the curve has a problem with clipping values. Let's analyze that. I don't know what the texture looping things are. Maybe they're looping. That could be. Let's try to... Okay, so we can clamp the curve sample coordinates and see what clamp GLSL. For people watching, be welcome. So it's X and then the 2 ranges. So curve sample coordinates, do we have to pass in? We can pass in a float. That's good. So we want this to be between 0 and 1. You know what? Maybe actually it should be 1 negative the curve lot half divided by curve lot sizes. Maybe that is already looping around. Nope, that is not doing it. Why? Let's do 1.5 pixels. Still not happening. You know, like the curve that I'm seeing here is doing stuff. Okay, I need to go to the toilet. Yep. Did I have a break thing yet? No, I didn't. Duplicate, break. Let's see. And then in the break thing, we're not doing the audio capture. We're adding in a bit of text that says that we're going to break text short break. Let's increase the font size by a ton. Oh, there we go. Let's put it right there. It's good. Okay. Okay, we're back. Let's see. So we're starting to figure out why the curve is causing these red, pink skies. I think maybe... No, I still don't know. So apparently a curve of, well, like a straight line curve does influence the color for some reason. Let's see, because if I apply it and or delete it, this is the difference. So it effectively did something. I'm just not sure what. As if, no, that's not the case. Let's go more crazy in terms of how much we're cutting off at the top. Still not visible. Okay, now I'm getting suspicious. Only sample half of the range. Okay, so it's... Wait, what? It's not doing anything useful here. It is still... I am so confused. Why? No matter what I do, it turns out to be pink. That's so weird. Okay, there's someone at the door. Okay, I'm back. Let's see. I was trying to figure out why the applying the curve compared to not applying the curve makes a difference, because I think what the curve should be doing right now is just the same as taking the effect color and clamping it between 0 and 1. And see, that does... Okay, wait. That does do the same thing. That does do the same thing. So the curve does it correctly, I guess. Why did that crash? Minimum splat. This one. What's wrong with this line? I don't see it. I don't see it. Unknown variable before curve call. Oh, I commented out the wrong line. Jesus Christ. So now we're trying to compare these two, and it's the same thing. So this means that the curve thing is doing its job correctly, I would say. And the sampler is indeed set to clamping. That's perfect. So then, if it's not the curve that does cause the issue, then what is? Right? So, okay. We're having this thing. Let's say we do effect color clamp. It's X and then the minimum and the maximum. Like that. That should do it. Okay. And so now with the curve enabled, I'm pretty sure that the color should diverge away from purple, like as we're seeing here. Like this. But not entirely as I expected again. For some weird ass reason. It's only at the very end that this happens. And now I'm thinking, is it due to the curve? Oh my god. Disable this. Oh. Oh, come on. So now it does work. I am so confused. Why does this happen? Right, so because right now it's white, and I think if I delete this line, it's gonna be red. There we go. So something clearly is wrong. Test. checking my audio real quick to check what it looks like, sounds like. Okay, that's good. Okay, let's try to figure this out. So this means obviously that the clamping, so right, we can't validate this. We're seeing places where the channels are bigger than one, so we can do that. Let's check mix again because I keep forgetting it. It's X, Y, and then the threshold. So X, Y, and then the, oh no, not the threshold, the blend factor, which is, so we're looking for a thing that's a, okay, now we need to look up the step function again. Wait, yeah, this is the step function, I don't need that. GLSL step. Edge comes first and then it's the value, so we're looking for something where this is bigger. Okay, so we're seeing several places where the clouds are brighter than 1, which is fine, I guess. What bothers me is that, okay, so effectively this is bigger than 1. That was what I was going to do. I was going to check that. So now it's a matter of figuring out where in the pipeline, where in the computations the red gets introduced. So we're not doing this. And now if we do this, it's gone. That's great, but I would like to understand why. So the curve shouldn't be the blame for it. So if we look at, yeah, so maybe it is the curve, because if I clamp before and I clamp after, wait a minute, that's the, isn't that the reason? That is the reason. I'm doing this, so I'm splitting it off into an effect color and then the original color, and then in the end I recombine them together to do some color preserving magic, and that's obviously where the problem comes from. There we go, that's it. So this is the reason we're seeing problems here is due to the color preservingness trick. But of course this color preservingness is completely wrong. Okay, so it's the color preservingness, which means, wait, but the Reinhardt tone mapping is in ProPhoto. That was the important part. Yes. Okay, so I'm convinced that it's the job of the tone mapping to make sure that it actually converges to 1, like that. So right now when I lower the exposure, it's gonna come back, and this is the behavior I was looking for. This is very much expected. By the way, to the people watching, if you have questions, just ask. I'm keeping an eye on the comment section. Okay, okay. So with this out of the way, let's start looking at the highlight correction. Ooh, look at that. There goes a lot of detail missing. Why is that? So this was clearly better, but why? Okay, wait a minute, what's happening? Let's re-enable the highlight recovery. Like that. It's ridiculous, but it's better than nothing. Let's see. So we're doing the tone mapping. LCS factor. Would that be a thing that we need to pass in? That's the contrast, but the contrast isn't 0, so that should not matter at this point. Eval homomorphic filtering. Yeah, so the homomorphic filtering is definitely at play here, but I'm curious as to why this thing is still influenced by it, because the highlight recovery, if we're not doing highlight recovery, then what is causing this issue? Oh no, look at that. Wait. Okay, this is reasonable. Let's try to find another photo with bright colors, probably, like this one. What am I doing? Is there anything else? Oh, look at that. This one is suffering a lot from the highlights problem. And it's bad because the tree is completely filling in the color of the sky. That is very bad. That is very, very, very bad. Okay, and then his face is probably coloring the sky as well for a little bit. So without the recovery algorithm, this is what we're looking at, which is bad, but then again, maybe this isn't as bad as we were thinking. However, let's try to examine the difference. What happens if we do this? We're seeing more, definitely, but is it better? Not sure. Not sure. There's just very little detail in this area, I would say. it's just bad because, okay, let's look at a color map. That is a one ridiculous color map. Oh, I don't like this. The more challenging photos are actually really challenging, it seems. So okay, there was this one technique where I was considering doing a fixed color sky, like I think it was this one. Yeah, and then I should of course enable the actual highlight recovery again. See, that looks better, but that's just because I picked fixed color. And it looks good in the sky, but it looks bad on the floor. I don't know. I don't know. I feel like there should be smarter ways to come up with the color map information. And highlight in painting. Like none of the highlight, like these things are all dealing with other things. Like even if you look at a paper like this one, please be available requests. Illumination based constraints into single into image in painting. Unlike occluded image regions filled by traditional inpainting, highlight pixels contain some useful information for guiding the in-painting process. Constraints provided by observed pixel colors, highlight color analysis, and illumination color uniformity are employed in our method to improve estimation of the underlying diffuse color. Yes, it's just that they are estimating the diffuse color, which is not what I'm doing right here. The inclusion of these illumination constraints allow for better recovery of shading and textures by inpainting. Experimental results are given to demonstrate the performance of our method. Let's see where this is originally published. IEEE? Okay, let's access this paper through university. No, that's not my login. Okay. I should really set up my VPN one day. Okay. Microsoft Research. Let's just quickly look at some of the results to see if or like the demonstrations to see if original image, saturated pixels indicated by blue, and user specific highlight area outlined in light green. After our in-painting procedure, final results after total variation in painting of saturated pixels. I mean, this is not, you can see like all of the information is there. It's not so much of a challenge. Well, I mean, I'm not saying it's not a challenge. This is just not what I'm trying to do. So that's what I thought. So let's go back and like try to find other resources. Saturated. So it's not removal. It's just like highlight estimation. Ooh, estimation of saturated pixel values in digital photos. Oh, and it's free. Look, okay, this is what we're dealing with. Clipping on raw RGB. Yeah. With saturation fixed. Look at that. So this is what I'm trying to do here. And they're doing it. I did something similar, but... Okay, so they're doing something Gaussian here. Algorithm evaluation. Please present some more clipping. Yeah, with saturation fix. Okay, this looks quite good. This does look good. Okay, what is this paper telling us? Let's read the abstract. Pixel saturation, where incident light at a pixel causes one of the color channels of the camera to respond to its maximum value, can produce undesirable artifacts in digital color images. We present a Bayesian algorithm that estimates what saturated channel values would have been in the absence of saturation. Yes, exactly. The algorithm uses the non-saturated response from other color channels together with a multivariate normal prior that captures the correlation across color channels. I see. The appropriate parameters for the prior may be estimated directly from the image data, since most image pixels are not saturated. Given the prior, the response of the non-saturated channels, and the fact that the true response of the saturated channel is known to be greater than the saturation level, the algorithms return the optimal expected mean squared estimate for the true response. Extensions of the algorithm to the case where more than one channel is saturated are also discussed. Wow, okay, so they're dealing with only one unsaturated channel, which is not good enough. But maybe it contains some interesting ideas, and they're saying it's being discussed. Both simulations and examples with real images are presented to show the algorithm is effective. From what year is this paper? 2004? 2007? Published and edited final as 2004. Okay. Let's skip the introduction. I know what the issue is. Saturation fix algorithm. The general Bayesian framework for estimation is well known. Here we develop the ideas specifically in the context of estimating the true value of a saturated pixel. Central to the Bayesian approach is the notion of using prior information. Here the relevant prior information is the joint distribution of RGB values, which we characterize by a multivariate normal distribution. Such prior distributions have been used previously in color image processing. although they fall short of capturing all of the statistical structure in natural images, they do allow us to express quantitatively the fact that there is a high correlation between the response of different color channels at each pixel. Yes, of course. Says that the R pixel value is plotted against the G pixel values after demosaicing for 500 non-saturated pixels. Randomly selected from a portion of the trunk of the image shown below. The level of correlation between the pixel types is dependent on sensor sensitivity, and scene content varies between for the images we have analyzed. In case of an N-color camera, the prior distribution of the camera sensor outputs characterized as an n-dimensional. Yeah, of course. Okay, so indeed, yeah, whatever. But this is probably an easier scenario. To simplify explanation of the saturation algorithm, we first assume that the image we start with is either full color or has been demosaiced, with the constraint that the demosaicing process only fills in sensor values missing in raw images and does not alter the raw pixel values. Therefore, for any pixel location we have Sn plus Nk sensor values representing different color elements of the pixel, Sn of which are saturated and Sk of which are non-saturated. In the pixel, yeah. Let us represent the true color values of the saturated sensors by an n times 1 column. Okay, let's reread that. Let us represent the true color values of the saturated sensor the means and covariances in equation 1 are obtained directly from the prior, Since we are only interested in estimating X saturated, we can simplify the calculations significantly by expressing the prior distribution only a distribution of X as conditional on the observed values of the non-saturated sensors yk. What is yk all of a sudden? So we're saying not saturated, which is determined by xk plus a random error term, where e is a column vector with independent and identically distributed noise elements. Oh, look at that zooming. Let's get a practical algorithm. Like, how does it know that it should be white and not anything else, like blue or... Because most of the image is either brown or green. Comparison of true sensor values from the saturated and summary and discussion. Alright, and we have presented a method for correcting the method base of estimation, although the implementation incorporates some compromises to decrease computational complexity. Both simulations and applications are real effective and it can greatly improve the appearance of images. We close with a few comments about possible algorithm refinements and extensions. A feature of our current analysis is that once the parameter of the prior established saturated pixels are corrected using only values from the other sensors at that location. Seems likely that additional information is carried by values at neighboring image locations, and that using this information would improve algorithm performance. One approach would be to employ the same theoretical analysis we developed above, but to apply it to image data from a neighborhood of saturated pixels. In this approach, we would specify a prior of the joined distribution of pixels, and by an image block, sure, and use the non-saturated pixel values within a block to correct saturated pixel. See, and this is like an extension that is too simple, because then you will run into the same issue that we're seeing with the clouds taking over the colors of other information around it. It's to estimate the parameters of from the local region of the image. If a portion of a bright red car is saturated, it makes sense to estimate the covariance of the sensor values using non-standard pixels that are spatially close to the saturated region and therefore likely to share the same color. For images with only a small number of saturated regions, this approach might also reduce the amount of calculation needed to estimate the prior covariance matrix. Finally, we note a different approach to dealing with saturated pixels is to avoid saturation during image capture. Yeah, of course. As discussed in the introduction, this is not desirable for conventional ADAR, since avoiding any pixel saturation typically forces most of the image a very small range of digital values. Indeed, the luminance range of natural scene is often as high as 40,000 to 1. Where was the discussion of the extension to more channels? I'm not sure if they're not using spatial information, then where do they get the covariance matrix from? To correct for saturation, the image was first demosaic, bilinear interpolation applied separately to each color channel. Prior distribution parameters were bootstrapped from non-saturated RGB values of the. We then applied the saturation fix algorithm. The algorithm was applied in order to green, red, and blue color channels. With saturation fixed, the flower color considerably closer to the original white. Near the nose. Where did they get the... Oh, here. We conducted a second set of simulations that presented a greater challenge for the saturation fix algorithm. These employed a different set of RGB spectral sensitivities where the color channels saturated at similar light levels. These sensitivities were obtained from an HB CMOS sensor. We used the same basic simulation method but employed Illumina D50 rather than Illumina D65. We again set the saturation level to 80% of the maximum sensor response to the 170 object surfaces. For this simulation, 9 surfaces had saturated colors, and for 7 of these, both the R and G sensor values were saturated. We used the same color correction and error calculation procedure as described in the previous section to process the simulated sensor response of the sensor. Table 2 shows the effect of saturation and the result of applying the base saturated fix algorithm. For pixels where 2 sensors were saturated, we used the sequential procedure described above. The result of the saturation fix are not as good as for a single saturation case, but this is to be expected given the greater degree of uncertainty when 2 sensors are saturated. Without the saturation fix, the color error range from with the saturation fix using the unbiased prior, the color error range between green gum and yellow yarn surfaces, both on which took a more yellowish hue after the saturation fix. Color images of rendered surfaces can be found. Overall, however, the saturation fix algorithm improved the color reproduction accuracy even though 2 out of 3 of the color channels are saturated. So yeah, I think basically they're estimating those parameters from the environment and are pushing it into a Gaussian mixture model, like, yeah. So let me think, how many parameters would you need to be able to correctly do this? Actually, this is pretty simple because they're only... Oh wait, it's not even a mixture model, it's a single distribution. Wait, I feel like... Okay, so you're... So this is 3, this is 3 by 3, all of that. However, the question, like, you wouldn't want to fit on the saturated thing because that's very nonlinear. I don't get the premise. On the intuition that in regions where some sensor channels are saturated, the non-saturated channels continue to provide useful information. In particular, there is in general a strong correlation, yes, so that the non-saturated values at an image location carry information that may be used to correct a saturated value at the same location. If the G pixel value is saturated but the R and B values are not, then the R and B values may be used to estimate what we refer to as the true value of the G pixel, that is, the value that would have been registered in the absence of saturation. Yes, our method is based on the principle of Bayesian estimation. A general approach that has been widely used to develop image processing algorithms. Since the algorithm operates in the raw sensor responses, it is intended to be incorporated in the camera image processing pipeline that is not appropriate for post-processing images already rendered. The algorithm is subject of a US patent. Interesting. Why would you patent such a simple thing? Let's see. Method and apparatus for estimating true color values of our saturated color values in the digitally captured image data. Let's find this patent. Worldwide applications. What's the status? Wait, does this mean... Publication? Application filed by Hewlett Packard? Wait, Hewlett Packard? I thought it was a paper from Microsoft. Hui Mei Zhang. Hui Mei Zhang, this is the one, yeah, indeed. It doesn't say... HP specifically, but... Other languages in French. What does this mean to be published? It's not granted, I guess? The legal status is expired. Okay, that's good. This is very old then. So this patent was filed in 2001, 2002, somewhere over there. And we're in 2020, so this is 18 years old. That is good, so this patent is no longer valid. So this thing expired, filing date 2001. Okay, so yeah, let's try to figure out where they get their estimates from the covariance thing. I think they're from an image. Largely achromatic. The truck image in figure 1. Okay. Ropes towing. The simple